Okay, we can start. We can consider now a nonlinear differential equation. We can write example y dot t equal to t to the power of 4 or y to the power of 4 of t. This expression is not linear in y. We can solve this differential equation writing the expression as dy over dt, which is y dot t by definition, times y to the power of 4t equal to t to the power of 4. So in this case we can integrate both sides by dt. This means that we can simplify, we can solve the integral in dy, the first integral. So this means that the first integral is y to the power of 5t or 5 plus constant c1 equal to the integral in dt of t to the power of 4 is t to the power of 5 divided by 5 plus the constant c2. So we can indicate the two constant as a constant c, and we get y to the power of 5 t of 5 equal to t to the power of 5 over 5 plus c, because c2 minus c1 is also a constant c. Then we find the general solution, which is y of t equal to, we can collect y of t is t to the power of 5 plus 5 c to the power of 1 over 5. This is the general solution because we have the constant c. If we want to know the particular solution, we can set some initial condition, for instance y at time 0 equal to y0. This means that using the general solution we have y0 equal to 5c to the power of 1 over 5, which means that c is equal to y0 to the power of 5 over 5. So the particular solution can be obtained substituting the constant c in a function of the initial condition y0, which means that yt is equal to t to the power of 5 plus y0 to the power of 5 to the power of 1 over 5. This is the particular solution because it depends on the initial value of y0. This kind of differential equation has no steady state solution because we can see in the formulation of differential equation there is no value for y which make the speed equal to 0. So there is no steady state solution in this kind of differential equation, also known as separable variable differential equation. Okay, now we can consider one of the so-called Bernoulli differential equation, which is y dot t minus 3t yt equal to t y to the power of 3t. In this case, we can divide both sides of this equation by y to the power of t 3 dt. Of t. In this case, we will get y to the power of minus 3t y dot t minus 3t y to the power of minus 2 of t equal to t. And this is the first step. Then we can define new variable z of t, defined as y to the power of minus 2t. This implies that the derivative with respect to time of z will be equal to minus 2 y to the power of minus 3t. We have also to derive y with respect to time, applying the chain rule, which is y dot t. So we can write this expression in terms of z as this part is, looking at this derivative, is minus 1 over 2 z dot of t minus 3t dz of t equal to t. And we can multiply both sides by minus 2, and we get z dot of t plus 6t z of t equal to minus 2t. Now we need this kind of differential equation is a linear differential equation. Z of t is 6. We have to multiply by the integrating factor, which in this case is e to the power of 3t squared, 3t squared, because we need to write this expression in terms of derivative with respect to time. In fact, this is d of z of t times e to the power of 3t squared with respect to time. The second one is minus 2t e to the power of 3t squared. Now we can integrate both sides with respect to time. This means that the first side is z of t e to the power of 3t squared equal to, this integral is equal to, you can check by yourself, is equal to minus 1/3 e to the power of 3t squared plus c. This means that the general solution for our differential equation in terms of z of t will be z of t equal to minus 1/3 plus c e to the power of minus 3t squared. This is the general solution, but in z. We need to find the general solution for our initial variable, which was y dot of t. The definition of z of t was z of t equal to y to the power minus 2t, which implies that y of t will be equal to plus or minus 1 over the square root of z of t. So the general solution for our differential equation, we have two general solutions with the two sides, which will be y of t equal to 1 over square root of minus 1 over 3 plus c e to the power minus 3t squared, and y of t equal to minus 1 over divided by square root of minus 1/3 plus c e to the power minus 3t squared. We have these two positive and negative solution. If y is positive, we will take just this solution. Now, if we want to check if there exists some steady-state solution, we can take again the differential equation y dot of t equal to 3t. We can use y star in order to identify the steady-state solution. plus ty star to the power of 3. In order to have steady state, we need that this expression is equal to 0, because we need that the speed of our variable should be equal to 0. In this case, it means that ty star times 3 plus y star to the power of 3 to the power of 2 should be equal to 0. The only steady state solution we can identify is y star equal to 0 from this expression. This is the only steady state solution. Actually, we can check the stability of this steady state solution computing in this expression the derivative of y dot respect to dy, which will be equal to 3t plus 3ty y square. This means that this derivative is always positive, and so we can in the phase diagram we will see that this solution will be unstable, globally unstable. In fact, if we compute the limit of these two expressions will be never equal to 0, because you finally you will get a negative sign under the root. You will have a complex solution. Finally, if we want to find the particular solution, we can set the initial value, and delete the breakpoint, y of 0 equal to y0, which means that in the general solution we get that y0 is equal to 1 over the square root of c minus 1/3. This means that 1 over y0 square is equal to c minus 1/3, which means that c is equal to 1 over y0 square plus 1 over 3. So we can write the particular solution as yt equal to 1 over the square root of minus 1/3 plus 1 over y0 square plus 1/3 e to the power of minus 3t square. This will be the particular solution of our differential equation, our nonlinear differential equation.